All right, let's talk about those beautiful, shimmering colors you see on soap bubbles or in an oily puddle. Ever wonder where they come from? Well, it's not dye, it's not a chemical, it's pure physics. Today, we're diving into this amazing phenomenon called thin film interference, and we're going to break down exactly how it works.
So, picture this. You're walking through a parking lot after it rains, and you see that slick of oil on the ground, shimmering with all the colors of the rainbow. It's something we've all seen, but probably never really thought about. It's not pigment, it's light itself, playing tricks.
So yeah, have you ever actually stopped and looked at one of those things and just wondered, why? Why those colors? And why do they seem to dance and swirl and change when you move your head? That's the exact mystery we are going to solve right now.
Okay, to really get this, we need to understand a couple of crucial things about how light behaves when it's not just zipping through empty space. These are the two key ingredients to the whole shebang. First up is this idea called the optical path. Now don't let the name intimidate you. Think of it like this. Imagine running 100 meters on a smooth, paved track. Easy, right? Now imagine running that same 100 meters through thick sand. The physical distance is the same, but the journey feels a whole lot longer and harder. For light, passing through something like water or glass is like running through sand. The optical path is how we account for that extra effort.
And here's the simple formula for it. The optical path is just the actual physical distance the light travels multiplied by this little Greek letter mu. That mu is the refractive index, which is just a fancy number that tells us how much a material slows light down. So a higher mu means more sand for the light to run through.
Now here's the second rule, and this one is an absolute game changer. When a wave of light bounces or reflects off a surface that's denser than what it was traveling in, say light in the air hitting water, the reflected wave literally flips upside down. It's called a 180-degree phase shift. This flip is so important because it means one of the reflected waves is now the exact opposite of the other, which is the perfect setup for them to cancel each other out.
So let's take those two ideas and see them in action. We're going to look at a classic physics setup, the wedge-shaped film. Just imagine taking two flat pieces of glass and putting a single human hair at one end. This creates a super thin wedge of air between them that gets thicker as you move away from the edge where they touch. Now, if you shine a single color of light down on this glass wedge, something incredible happens. You don't just see a plain reflection. Instead, you get this pattern of perfectly straight, parallel, bright, and dark bands. We call these fringes, and each one of these fringes corresponds to a line where the thickness of the air wedge is exactly the same.
So why the bright stripes? Well, they show up in places where the two light waves reflecting inside the wedge meet up perfectly in sync. Peak lines up with peak, trough lines up with trough. They basically give each other a high five and get brighter. We call that constructive interference. This formula here is essentially the recipe for brightness. It's telling us exactly what thickness d is needed for a specific wavelength of light lambda to create a bright spot.
And the dark bands? You guessed it. That's the exact opposite. This is where the two reflected waves are perfectly out of sync. One wave's peak meets the other's trough, and they completely annihilate each other, leaving nothing, darkness. That's destructive interference. And look at the formula. It's almost identical to the bright one. The only thing missing is that plus 1/2. That tiny difference, which comes from that 180-degree flip we talked about, is literally the difference between light and dark.
I know this diagram looks a little busy with all the angles and lines, but the big idea is actually pretty simple. All it's doing is tracing the paths of the two light rays, the one that bounces off the top of the air wedge and the one that goes through, bounces off the bottom, and comes back out. It's the difference in the length of those two journeys, plus that one flip, that determines everything.
Okay, so we know how these fringes form, but the really cool part is what they can tell us. These patterns aren't just pretty to look at, they are packed with information. It's like we're learning to read the language of light. The source material really nails it here. Right at the very tip of the wedge, where the two pieces of glass are physically touching, the thickness is 0. And at that point, the fringe is always dark. Always. Why? Because with 0 thickness, the two light paths are the same length. So the only thing separating them is that 180-degree flip one of them made. That flip guarantees they're perfectly out of sync and will cancel each other out every single time.
And the spacing between these bands, that's what we call the fringe width. It's not random, it's a direct measurement of the angle of the wedge. A really steep wedge angle will squish the fringes close together. A very shallow wedge will have them spread way far apart.
And this is where it gets incredibly useful. With a perfectly flat, perfect wedge, you get these perfect, straight, evenly spaced lines. But what if one of the glass surfaces isn't perfect? What if it's got a tiny bump or a dip? Well, the fringes will bend and curve around it. The pattern literally becomes a topographical map of the surface, revealing imperfections that are way too small to see with the naked eye.
Okay, everything we've talked about so far assumes we're using one pure color of light, like a red or green laser. But that leads to a really interesting question. What happens if you just use plain old white light, which, as we know, is actually a mix of all the colors?
And here it is. This is where we come full circle, right back to that puddle of rainbows. That central fringe, at 0 thickness, it stays dark, no matter what. But for all the other fringes, something amazing happens. Each color in the white light has a slightly different wavelength. That means the blue light creates its bright bands in one spot, the green light in a slightly different spot, and the red light in another spot still. The fringes split apart into a beautiful rainbow spectrum. And that is exactly what's happening on the surface of a soap bubble or in a thin film of oil.
So this ability to predict and control how light behaves isn't just for making pretty colors or measuring tiny bumps. We can actually take this principle of perfect cancellation and use it to make reflections literally disappear. It sounds a little like science fiction, but it's very real.
Just think about that for a second. If we know the exact recipe to make light waves cancel each other out and create darkness, what could we do with that power? Where would that be useful?
Well, the answer is non-reflecting coatings. You almost certainly have this technology on you right now. It's on your eyeglasses to reduce glare, it's on camera lenses to get clearer pictures, and it's on solar panels to capture more energy. The whole point is to use this physics to engineer perfect destructive interference and kill unwanted reflections.
So here's the trick. Engineers apply an incredibly thin, transparent coating to a lens. The material and its thickness are calculated with insane precision. It's designed so that the light wave bouncing off the top of the coating is perfectly out of sync with the wave that bounces off the bottom. Just like the dark fringes in our wedge, those two reflected waves completely cancel each other out. The reflection is destroyed, which means more of the light you actually want to see passes through the lens, giving you a much clearer view.
And that's really the big takeaway here, isn't it? It all started with just being curious about a rainbow and an oil slick, and it ends with the technology to make reflections, well, invisible. By perfectly understanding the fundamental rules of how light waves interfere, we can control them to do incredible things. It really makes you wonder, what other secrets are hiding in plain